What's up, everyone? I've implemented a lightweight version of Redis, and I would like to share and study with you everything that I learned during this process. The first thing is to deeply understand what is a Redis application. It is a standalone application, and it is an in-memory storage, and also in-memory storages are great for caching. That's the main capabilities of Redis. As a standalone application, it means that it's an application that is separated from your main application, right? As you can see in the diagram over here. So it is a different process, it has a different memory space, so it's a completed isolated application. And we can have a basic contact with Redis just installing it in your computer. I already have it installed over here, but it's not running. But I will start the Redis service. Redis has also a tool, the redis-cli. So this is the redis-cli, which is a separate application. So this one is not part of the Redis service, and we can run a bunch of different Redis commands. As I said previously, Redis is in-memory storage, so we are able to store information over there. It's key value store, so I can try get, for example, my key, which is, we don't have any key with this specific name, but we can try to set it any value just to have an example, and then when we get it, okay, it's working. If we stop the service, this will stop working as well, as you can see over here. If we start again, you notice that it is an in-memory storage, but as we stopped and started again, we still have that value. This is a capability that we explore further, but this is just one of the Redis clients. We also have other types of clients, the ones that we can use in our own applications. For example, over here I have a Python script, so I already have the Python Redis library installed in my environment, so we can import like this. We can create a new client like this. It will point to the default host and port, that's why I don't need to pass anything. And we can try to get the value of a specific key, so in this case the my key, and that's it. Here's the value. So we have like different clients pointing to the same data store. That's the purpose of Redis. Now we can explore another aspects of the application. It also have features of message brokers like queuing and pub/sub, but this is not the focus of Redis. The most used features are related to those in-memory storage and also the in-memory caching, right? Because RAM is faster than disk, so this is why we use a Redis for caching. So if you see this type of architecture, it's pretty similar to a regular database like Postgres or MySQL. The difference is that we don't have that SQL part, the relation between tables, and those databases will store the information on disk, and Redis is going to store that in memory. But the thing is, why store things in memory? Okay, we know that memory is faster than disk, but how much faster? I prepare a local benchmark. It's running on my own computer. It's also available on GitHub Gist. The link will be in the description below. Let's run and see the results. While the benchmark runs, let's take a look at the code of the benchmark to have an idea what we are going to test. We have different scenarios based on the size of the information that will be stored. The very small scenario is just 1 kilobyte, the small is 100 kilobytes, the medium 1 megabyte, and the large 100 megabytes. We have a couple of functions to help us execute the benchmark. This one's responsible to generate the data. So this number over here, it's actually being passed to the function because this is generating data, a string that will have the number of characters of this parameter, the size. And each one of the characters will be a random ASCII2 letter plus a digit, simple like that, and will be encoded in UTF-8. There is this other functions that will write the data into the disk. This other one just reads the data from the disk. And we have those two benchmark functions, the benchmark ran and benchmark disk, that will be responsible for reading the data. In case of the memory, we'll just do this hack with Python. This will force Python to actually read the data from the memory. And for the benchmark disk, it's a little bit simpler because we just need to read the data from the disk, from the file. And to do the benchmark, we will loop through the scenarios. You generate the data based on the size of that scenario. We are going to write it to the disk, and then we benchmark the RAND, and we benchmark the disk. We compare the results and just append to this results list, and then we just print the report. We already have the results for the very small scenario where I only have 1 kilobyte of data. The RAN time is actually 14 times faster than the disk performance, and we can see that this grows a lot based on the size. So bigger the size of the information on the disk, better the performance. This is interesting because usually we think about the files in the folders structure. Like one folder has more folders, which has files. We may think that this file will be saved in the disk, like close to each other in a contiguous way, but this is not the case because we have different segments. So if the file is big, it's probably different segments that are not close in each other in the disk. So for a case of a hard drive, you have a mechanical move that must be done in order to read the data. So this would explain why this is really slow. Anyway, my point is that we have a lot of different variables and abstractions on top of that may influence in these times. Usually when doing those implementations, we have more complex scenario, a bunch of different combinations of different access to the information and read and so on. But for this very control scenario, when we change the input, the size, we actually have a different ratio between the results. We can see that larger the file, it's really worse the performance for reading from disk. We have this article that I would like to read it with you. MySQL as Redis versus Redis. This is the next portion of my research around my UUID set cache. This is a non-sequential timeline. I already read the article. We have some aspects related to Java technology that I'm just going to not read it at all and keep it out of the final cut, but you are free to read it later. It do not impact the purpose of why we're reading it. What are we testing? My use case is simple. I have a large in-memory set of UUID, around 1 million keys. This is how I'm going to start it in MySQL. Create table set 1M. We have an ID, binary 16, not new primary key column, and that's it. A code to convert UUID to binary 16, which is just an array of bytes in JDBC. We have the array, we have this byte buffer, and we're going to put the value, which is the UID. We get the most significant bits, guess the least significant bits, and that's it, and return the array. Benchmark. Benchmark code is relatively simple. N threads take UIDs one by one and make a simple query. Select one from set 1M where ID equals the ID that we're trying to find. I benchmarked for 1 thread to 10 threads. The comparison between the MySQL and Redis, let's go. Predictably, Redis has better performance than MySQL. Even though data set in MySQL is really small, hundreds of megabytes, overhead of SQL seems to be significant. So we have the results here. So MySQL, like more than, I think, 4 times worse than the Redis. This is way better than our best case with small files. In the benchmark, for the very small, with 1 kilobyte of data, we had like 14 times faster improvement when reading RAM and reading from the disk. And over here, this comparison between Redis and MySQL, it's around 14 times better. The Redis is 4 times better than MySQL. And if you look at the maximum request duration, it's even worse, meaning that MySQL consumes much more CPU than Redis. Oh, this is the comparison. So in this line over here is, which is this axis over here. I don't know which is this information. Here, of course, is the max duration in microseconds. Redis versus MySQL set 1 million. This one is microseconds, but what is this? Maybe the size of records in the database? I don't know, I don't get it. Conclusion. For sure, MySQL doesn't fit this use case at all. It makes a lot of sense. The strength of MySQL isn't here, but in stability, replication, transactions, and many more. It was fun, as usual, to benchmark different aspects of MySQL. I'm also happy that I don't need to write housekeeping code for thread local connection pool to benchmark it. I guess it was more than 4 years in my backlog, because I would rather explore async access to MySQL and not blocking. Full data shards for MySQL and MySQL versus Redis source code is on GitHub. So this is the article written by Dmitry Komanov. So take a look on it afterwards. But let's go back into the other characteristics that we have related to Redis. We took a look on this RAM versus disk and see that in fact, RAM is faster than disk, but we have a lot of different variables that will impact how many times is the RAM faster than disk. That depends, and just need to benchmark in a specific scenario. If we implemented different benchmarks between Redis and MySQL, we probably get different results, and it's almost impossible to simulate a production service because we have all the chaotic nature of a system and people using those systems and everything. But anyway, as we have seen before, the application, it's separated from the Redis server. So Redis is not like a library that we install in the application server and use this library inside of the application server. We do have the Redis library as we use it in the Python script. This one. We can import Redis, and we can create a new client, and then we can try to get a value from a specific key, and that's it. But this is not the Redis server. It's just a library. It's just a library that helps doing the client part, so we don't have to implement the Redis protocol from scratch, which we are going to look afterwards. We need some form to communicate between the application server and the Redis server. This communication is done by the TCP protocol. So Redis listens TCP connections in a specific port, and our clients, which is their applications, will connect with Redis in this port and will exchange information with the Redis server. Let's take a deep look in the TCP protocol. I have prepared a couple of characteristics from the TCP protocol. So the TCP establishes a reliable end-to-end connection before data transmission starts via three-way handshake. So it's basically, oh, I want to send information to you. Do you accept me? Okay, you can do it. And then a third handshake is done. Okay, so let's start it. It's something like this. I don't remember from scratch, but you take a look at it later. It ensures that all data packets are delivered accurately and in order. This is really important because it doesn't matter if we send all the pieces of data, all the bytes that we want to send when we do this command over here, for example. So we are asking Redis to return the value of a key called my key. So it doesn't matter. We are going to split this in different bytes and different packets of information. We need to send that in the correct order, and TCP will solve that problem for us. TCP connections are also full duplex. It allows simultaneous two-way data exchange between the sender and the receiver. So it's different for HTTP that there is this concept of request, and only the client sends a request and receive a response from that request, but the server cannot communicate with it afterwards. The TCP protocol also implements congestion control, so it will implement mechanisms to prevent network congestion. It properly closes connection using a four-way handshake to ensure no data is lost during the shutdown. Different from HTTP, here we have no concept of request or comment or a message. So it just sent and received bytes. It doesn't care which information is there in those bytes. It doesn't know which each one of those bytes mean. It's just send and receive it. And it's like a string of data that is always open. Imagine like you are on top of a river and another person is down a river, and we start like sending those, I don't know, paper maybe. You send so paper boats with zeros and ones, and the person over there is just collecting those paper boats. We don't know where the message starts and ends. We just have those paper boats. So we must have some sort of protocol that is outside those river, that is outside this boat. And that's the case over here because TCP doesn't provide this for us. This is for the developer, the programmer of the application, to implement a protocol and deal with it. Computer Networks from Tenenbaum is an awesome source for a deep dive on how TCP works. This is how I learned a couple of those things that I put over here. I have the book opened, so I highlighted a couple of parts. Let's read it together. Each machine supporting TCP has a TCP transport entity, either a library procedure, a user process, or most commonly part of the kernel. Transport entity, TCP transport entity is part of the kernel. So in that case, it doesn't matter which programming language are we going to use, because all of them will have to delegate to the kernel. In all cases, it manages TCP streams and interfaces to the IP layer. A TCP entity accepts users' data from streams from local processes, breaks them up into pieces not exceeding 64 kilobytes in parentheses, often 1460 data bytes in order to fit in a single Ethernet frame with the IP and TCP headers, and sends each piece as a separate IP datagram. We have a lot of different words. This is low-level stuff that is not the purpose of this video, but we have all those information in these other parts of the book. The IP layer gives no guarantee that datagrams will be delivered properly, nor any indication of how fast datagrams may be sent. It is up to TCP to send datagrams fast enough to make use of the capacity but not cause congestion, and to time out and retransmit any datagrams that are not delivered. Datagrams that do arrive may well do so in the wrong order. It is also up to TCP to reassemble them into messages in the proper sequence. TCP service is obtained by both the sender and the receiver, creating points called sockets. Each socket has a socket number, an address, consisting of the IP address of the host and a 16-bit number local to that host, called a port. When I was younger, I usually think as this socket as a physical thing, right? But we can have many different sockets, basically one for each port that we have in our machine. And we don't have those different physical connections. All that socket thing is just an abstraction. It's just software. In the end, we are just transmitting bits in our network hardware, and that's it. A port is the TCP name for TSAP. For TCP service to be obtained, a connection must be explicitly established between a socket on one machine and a socket on another machine. A socket may be used for multiple connections at the same time. Two or more connections may terminate at the same socket. Port numbers below 1024 are reserved for standard services that can usually only be started by privileged users, e.g., root in Unix systems. They are all called well-known ports. Here we have an example of those well-known ports for the FTP, SS80, SMTP, HTTP, and so on. All those protocols that you probably have used. All TCP connections are full duplex and point-to-point. Full duplex means that traffic can go in both directions at the same time. Point-to-point means that each connection has exactly two endpoints. TCP does not support multicasting or broadcasting. A TCP connection is a byte string, not a message string. Message boundaries are not preserved end-to-end. For example, if the sending process does 512-byte writes to a TCP string, this data may be delivered to the receiving process as 512-byte chunks, 2 1024-byte chunks, 1 2048-byte chunk, or some other way. There is no way for the receiver to detect the units in which the data were reading, no matter how hard it tries. The TCP software has no idea of what the bytes mean and no interest in finding out. A byte is just a byte. When an application passes data to TCP, TCP may send it immediately or buffer it in order to collect a larger amount to send at once at its discretion. However, sometimes the application really wants the data to be sent immediately. A user of an interactive game wants to send a string of updates. I'm showing this information directly from this awesome book from Tannenbaum. It's basically the same thing as we have in our mind mapping on ScaleDraw to do this video. I couldn't find any source on online articles, or Google search, or in ChatGPT that had this quality of information from this book. This is why I'm showing and reading that with you, so we could know that this book exists, this book is awesome, and you can use that for researching. The commands and the responses are being sent and received by network calls. We're just sending bytes over the wire, but to send commands and receive responses, the application server and the Redis server will communicate sending bytes to the wire with this TCP connection. But we have seen some limitations of the TCP protocol, and that's why Redis has the Redis protocol. It's a protocol on top of TCP that will organize how this information will be exchanged between the client and the services. In the Redis protocol, the data is human readable. It's basically a serialized string. The string is not a plain text, but a structured string defined by the Redis protocol that we'll take a look in a second. It was nice to implement such protocol from scratch because I most worked with things like JSON, and probably every programming language has a JSON module. So in Python, for example, it's really simple. We just need to import JSON and then just call JSON.loads. I'll put a key, A, and the value 1. That's it. I just need to escape, and that's it. If you think about this is a complex problem to solve, because okay, the first thing would see if you have an open bracket and a closing bracket, and then we check all the keys that we have inside, if the keys are separated by blah. Let's take a look into the Redis protocol. I already have the link here. Let's read it together. Redis serialization protocol is the wire protocol that clients implement. To communicate with the Redis server, Redis clients use a protocol called Redis serialization protocol. While the protocol was designed specifically for Redis, you can use it for other client-server software projects. RESP is a compromise among the following considerations: simple to implement, fast to parse, and human readable. RESP can serialize different data types, including integers, strings, and arrays. It also features an error-specific type. A client sends a request to the Redis server as an array of strings. The array's contents are the command and its arguments that the server should execute. The server's reply type is command specific. RESP is binary safe and uses prefixed length to transfer bulk data, so it does not require process bulking data transfer from one process to another. RESP is the protocol you should implement in your Redis client. I think it's because the Redis can be a cluster, so in that scenario there is communication between the different nodes of the cluster. I think that's it, but I'm not sure. While RESP is technically non-TCP specific, the protocol is used exclusively with TCP connections or equivalent string-oriented connections like unit sockets in the context of Redis. Request response model. The Redis server accepts commands composed of different arguments. Then, the server processes the command and sends the reply back to the client. This is the simplest model possible. However, there are some exceptions. Redis requests can be pipelined. Pipelining enables clients to send multiple commands at once and wait for replies later. We don't care about pub/sub. Let's go further. We don't care about the monitor. This relates to that TCP characteristic that we were talking a couple of moments ago. RESP is essentially a serialization protocol that supports several data types. In RESP, the first byte of data determines its type. Redis generally use RESP as a request-response protocol in the following way. Clients send comments to a Redis server as an array of bulk strings. The first and sometimes also the second bulk string in the array is the command's name. Subsequent elements of the array are the arguments for the command. The server replies with a RESP type. The replies type is determined by the command implementation and possibly by the client's protocol version. RESP is a binary protocol that uses control sequence encoding standard ASCII2. The A character, for example, is encoded with the binary byte of value 65. Similarly, the characters CR, LF, and SP have binary bytes of 13, 10, and 32 respectively. I think this is really confusing because when we think about a byte or a binary, I expect to see a couple of zeros and ones. I know this is like an integer representation of a binary, a byte. But anyway, it's very confusing. I have written the challenge in Golang, and every time I was printing the value of this byte, it just showed this integer number, and it was pretty confusing. But anyway, the CRLF is the protocol's terminator, which always separates its parts. The first byte in a RESP serialized payload always identifies its type. Subsequent bytes constitute the type's contents. We categorize every RESP data type as either simple, bulk, or aggregate. Simple types are similar to scalars in programming languages that represent plain literal values. Booleans and integers are such examples. RESP strings are either simple or bulk. Simple strings never contain carriage return or line feed characters. Thank you for showing the acronym name. I hate acronyms because sometimes I don't remember the acronyms. Sometimes I don't know how to pronounce the acronym, like SQL, SQL, I don't know. Bulk strings can contain any binary data and may also be referred to as binary or blob. Note that bulk strings may be further encoded and decoded, e.g. with a wide multi-byte encoded by the client. In my implementation, I didn't cast like the value of a key, for example, into a string, because I just received the bytes over the network and I just stored the bytes and that's it. This is interesting because that way we could store images, we could store files and other bunch of different information that is not text. Anyway, I know that we can like cast an image, a PNG and JPEG image into a string version of that image, but I didn't want to do that. Aggregates, such as an array and maps, can have varying numbers of sub-elements and nested levels. The following table summarizes the RESP data types that Redis supports. The first byte is what will tell which type of data type we're going to serialize. And here in this table we have it. So for simple strings, we have the plus sign. For simple errors, we have the minus, the subtract sign. For integers, we have this one. For bulk strings, I have the dollar sign. For arrays, I have this one. For nulls, this one. And that's it. Let's start with a simple data type, which is the simple strings. Simple strings are encoded as a plus character followed by a string. The string must not contain a CR or LF character and is terminated by a CRLF. Simple strings transmit short, non-binary strings with minimal overhead. For example, many Redis commands reply with just OK on success. The encoding of this simple string is the following 5 bytes. When Redis replies with a simple string, a client library should return to the caller a string value composed of the first character after the plus up to the end of the string, excluding the final CRLF. We could like just return plus OK. So think about it. Why do we need to send that CRLF character at the end of the message? Why we need to do that? It's because of the problem of the TCP that we don't know where the message ends. We don't have the concept of comment of the message or a request as we have with HTTP. We need to use a special character to separate the message. Similar from we do with text. For example, we are just separating some informations as a full text spreadsheet. For example, ID, and I use the pipe and my name, and my dog is barking a lot. I don't know if you're listening to it, but I continue anyway. And here we have the ID and we have the number. So we are using this special character. We know that in the column name, I will not have this special character. I can't have a column called like this, for example. This character is banned. Got it? If this were like HTTP, which have a beautiful and ready to use request, we wouldn't need those two characters. Simple errors. RESP has specific data types for errors. Simple errors are simply just errors, are similar to simple strings, but their first character is the minus character. The difference between simple strings and errors in RESP is that clients should treat errors as exceptions, whereas the string encoded in the error type is the error message itself. The basic format is we have the minus character, error message, and the termination. I just call it termination because I never... We have this other type, which is the integers. It represents a base 10 64-bit integer. RESP encodes integers in the following way. We have the column. It is the first character that indicates that this is an integer. We have an optional plus or minus as the sign, one or more decimal digits as the integer's unassigned base 10 value, and the terminator. For example, we have the 0 and the 1000. Those are integer replies of 0 and 1000 respectively. Many RESP commands return RESP integers, including increment, len, last save, and so on. So you might be thinking, why? Why just separate like this integer value? We could just use this type of value over here. One of the reasons to do that is because we will use less bytes if you use integers. There's one thing that I didn't know, and I learned right now, because we just send bytes, 8 bits for 8 bytes, zeros and ones in the network. The meaning for those bytes is just arbitrary. Numbers, for example, are composed by one or more symbols. And for those situations, we will use more bytes with a string than we use with an integer. So for example, let's get the number 100. Okay? The number 100. We can have the number 100 and we can have the string 100. But if we generate a binary representation, and my string is wrong by the way, if we generate a binary representation to represent in binary the number 100, we are going to use only 1 byte. But with a string, like a string is an array of characters. So we need to represent each one of those characters independently. So that string will have 3 bytes. You don't trust me? Just let's do an experiment. We have this function that casts the data into a binary. Just asked ChatGPT to do that, and in ChatGPT, we trust, we always trust. So we have the string 3 bytes. But if we do that with the number, we only have 1 byte. Okay? That's probably one of the reasons behind that. I don't know if there is other reasons behind that. Bulk strings. A bulk string represents a single binary string. The string can be of any size, but by default, RESP limits it to 512 megabytes. See the Proto-Max bulk length configuration directive. RESP encodes bulk strings in the following way. We have the $sign, then we have the length that will be a number. We have the terminator used as a separator, which is something new in the protocol that we haven't seen until now. We have finally the data and then the terminator. The string hello, for example, would be encoded as follows. I mean, at this point, I'm not sure if this number here is that useful, but for sure it helps in the implementation because we could like cut it by index. It can help, but we could know that the first character here after this separator would be the command. But we will see that when it starts nesting those types of data types like bulk strings, you see that this number will be really helpful. Arrays. Clients send comments to the RESP servers as RESP arrays. Similarly, some RESP commands that returns collections of elements use arrays as their replies. An example is the lrange command that returns elements of a list. RESP arrays encoding uses the following format. We receive the asterisk, then we have a number, then we have the separator, then we have a list of different elements that will be separated by the separator, and we know like the number of different elements that is based on this value over here. So this integer is very helpful that we can implement that thing, and it will help to check if the information is correct, because if you don't have this number over here, we don't know where the comment ends. Let's see an example of this. So this comment over here, it's the comment hello world. So we have the asterisk, and then we have the number 2. If you don't have the number 2, if we receive, for example, this string over here, just let me get the text editor. So if you don't have this, this looks like a correct message. This is why this number is important, because if we receive that, we know that we are missing one of the arguments on the message, which in that case is the word. As you can see, after the asterisk, the CRLF part prefixing the array, the other data types that compose the array are concatenated one after the other. For example, an array of 3 integers is encoded as follows. Good stuff. Arrays can contain mixed data types. For instance, the following encoding is of a list of 4 integers in the bulk string. Okay, now that we have the arrays, basically we have all the information to understand a simple command as the set or the get command. So let's go back. Every time we do this thing over here, the command will be something like, just let me get this one to help me. But there is the thing. So here we would have the get command. This would be like 3, and then we would have the name of the key. For example, my key, which is 5 characters, and that's it. That's what we are going to send in the network. Actually, a binary representation of this, it's what we are going to send in the network. That's what we're going to send in the network. Going back into our mind mapping, this character and the number of characters are very useful to serialize the comments, and because those comments are being transmitted with TCP, so we can see that the technology where the protocol is being used influences its design. Those things are entangled, you know. Oh, I forgot that part. But why a standalone application? Because if we have this in-memory server, we store the things in memory. But our application server already have memory. So why do we need a separate application which is harder to maintain, which puts complexity on the architecture? Why? Why do that? Crashes does not kill the application server. For example, if we start storing some heavy objects which will consume all the memory from the server, if we are storing this information directly into the application server, will kill the entire application. And this will impact not only the features that rely on the cache server, but also all the features that are encapsulated in that server. As each application server has its own memory space, the objects can be shared between the different application instances. That means that the memory users will be like multiplied by the number of instances that you have, as each instance will need to cache its own object. And like you probably have a load balancer that will distribute that request between different instances, so we could send to a server that has not that object cached. So we have this problem with performance, because usually when using cache, we are using another database to retrieve the information to be able to cache it. So in that case, we would put more pressure into the main data storage, and we will also multiply the usage of memory. So this is the problems of using the cache in the same server as the application. So just implementing, for example, a global variable. But if you have a very simple application, or we just have one or two instances of our application, this is a valid solution. Django, for example, has this one by default. So you put over here Django cache in memory. Okay, whether in the database or the file system or directly in memory. Local memory caching. This is the default cache if another is not specified in a settings file. If you want the speed advantages of in-memory caching but don't have the capability of running main cache, consider the local memory cache backend. This cache is per process, see below, and thread safe. To use it, set the backend, banana. What I'm trying to say is that there is some cases where this is actually a better solution than using an external server. This is why it's important to understand why do that in an external application. We talked about this in-memory storage feature of Redis server, but we use databases like Postgres or MySQL that use a real disk to store information because memory is not reliable. Once the computer restarts, or if the server restarts, we lose all the information that are allocated in the memory. But there is some situations where it's acceptable to lose information, like not all information, but some recent information. This is why Redis have this concept of snapshots. A snapshot periodically saving memory data to disk. But this is not just useful for having a permanent data storage. This is important to keep the cache working as expected, because this enables a quick recovery of cache data after a restart. So if I have a snapshot and then I start the server again, we are going to be able to populate all the information that was allocated in the cache before the crash or the restart. Restored snapshots prevent sudden spikes in traffic to the main database when Redis is used as a cache. Imagine that we have a homepage of a news website, for example, that has a lot of traffic, that we have a lot of requests being done to retrieve the news information, and we use a cache to do that. But the cache just crashes. All those, I don't know, maybe 500,000 records that were stored in the cache just is lost. That means that after that, all the traffic from this website will be directly to the database, and the database is probably not able to handle that. That's the purpose why the cache was put in front of the database. So this will make the database probably crash, or will impact the performance of other things. So the snapshot is very important for that as well. It will minimize the data loss during crashes or restarts. This could be important for applications that don't care if you lose like information that were reading the last 5 seconds, but once you keep all the other data, that's probably fine. And we could use, in that case, Redis as your primary data store. That's what I'm saying in the last topic over here. Some applications are tolerant to some data loss, and features like snapshots allow Redis to be used as the main databases. I also implement this snapshot feature, and that's a good hook for my implementation. I have a couple of things that I annotated over here. In my Golang implementation, which was easy to implement the concurrency part because of the Go coroutines. It was really easy, and Go is not my primary programming language. The storage implementation was pretty simple as well. I just implement a global map variable where the key is a string that we receive in the command to set the key value, and the value is just a slice of bytes, and I just store this slice of bytes related to that key, and that's it. Golang exposes this buffer idea when we read data from the TCP connection on its own API, which is different from other implementations. Let's take a look in the code together, and we explore the decisions that I took and how I implemented it. Here's the code. I have a couple of abstractions and functions. The code is not that big, but it's like big enough to understand in just a few minutes. It's actually 500 lines. This is where all starts. I just import the start function from the server package, and this is where it all starts. So the first thing that we do when we start this Redis implementation is to restore the snapshot. If there is some error trying to do that, you just print the error and move on. And next we start to listening to connections on TCP in the local host on the 6379 port. This is the default port, by the way. If there is any error trying to listen, then we just need to stop over here because you're not able to handle the connections. Then I started this Go routine to periodically save snapshot. We'll take a look at that later in the snapshot implementation. And then we start to accept the TCP connections. If we have any error accepting a TCP connection, we just continue because we could succeed in the next attempt. And once that we establish a connection, which means that there is a client. So every time, for example, we do things like this, we are opening a connection. I will handle that connection in a Go routine. That means a green thread. So each one of the connections will be a green thread in that implementation. And that's it. We keep on doing that until an error occurs or until we kill the application. Let's take a look into this handle connection function. The first thing is that we are going to close when everything executes over here. We defer the connection close. And then we start this abstraction, the deserialization buffer. Why this deserialization buffer is important? Remember, we don't have the concept of command and message with TCP. Maybe I'm being redundant because this was difficult for me to understand since I just worked with protocols like HTTP where you have the command encapsulated into the request and so on. When we read bytes from the connection, from the wire, we have no guarantee that we have the entire data of one comment, for example, to get or set a key, or that we get only one comment. We could get two comments, for example. This is why we need this deserialization buffer, because we'll keep reading and joining all this information into the buffer, and later we'll try to extract the comments from the buffer. It's not so simple as just read. We can't like get this information over here and like this connection buffer and then assume that this is the comment. And that's why we do have this method called absorb. We are getting the bytes that we have read right now, and we are concatenated with the bytes that are already in the buffer. That's what this absorb function does. It appends the bytes read from the network to the existing data in the buffer. The implementation is a little bit more complex. You can take a look on it, but the concept is simple as that. Once you have absorbed all the bytes that we read from the network, we are going to try to dissipate, to extract the commands from the buffer. And we need to do that until we remove all the comments from the buffer, because as you can receive more than one comment in one read from the network, and you can have partial comments that was left in behind in the buffer and so on, we need to do that. And this is why you have this for loop over here. So for there is comment in buffer, we are going to do that. We're going to dissipate. So we dissipate, so we get the result, and this will already parsed. So we have this deserialized command, which we have in the result arguments over here, and based on the first argument, we will know which comment we need to do. If we go back into the REDS serialization protocol, the first byte is actually the data type that is going to be serialized, and the next things will be the arguments. Here we already have all the arguments from the command. In that case over here, these arguments would be just a list of strings or bytes where we have get, and the second data will be my key. That's it. This is why in this factory called get comment, we are using only the first index, because we are getting, for example, the get, the set, or the other command. What this function does is just check which type of command we need to execute, and will just returns this command structure that implements a command interface. We have the command set, the command get, the command ping, the command echo, and so on. Just to check what is the get byte array. So this is the get, it's the binary version of the string get, simple like that. And then if we get the command successfully, we just execute the command. Let's use the get, command get as an example. So to execute that, we will receive the message with the array of bytes. That's get my key. The my key will be in the argument index 1, and we just go in the cache and load that information. If we could load that information correctly, we just serialize the response. If not, we will serialize an error. And each function, that serialization, it's an implementation of the Redis protocol. So that part is the serialization, is where we have the string in memory and we want to cast that into the response. But we also have the deserialization, that is the process of receive a message like this and transform into those array of arguments that we have seen in a couple of moments ago. And that implementation is here somewhere. This deserialized function, it's what receives that command over here like this in an array of bytes form, and will just serialize into that deserialization result, which will have also an array of arguments, which is the form that we just seen a couple of moments ago. Right here is where we check like the first item, the first byte, to check the type of deserialization that we are going to do. If you remember in the REDS protocol, each type of data that you're going to deserialize, you have the error string, the bulk string, the array string, and so on. So the first byte is used to determine what is the type, the data type that will be deserialized. And we have that part over here because it's a recursive function, so it's complexity that I just jump into this session over here, but you can check the code, is open source on GitHub, try it later. And we have specific implementations for each data type. We have the deserializer interface, and each one of those specific data types has its own deserializer. When our deserialized buffer is extracting the comments from there, it will going to use the deserialization. So if you go into the deserialization buffer, I left a couple of comments over here. It's a buffer that handles TCP reads. As Tannenbaum explained in his book, Computer Networks, TCP is not a message protocol but a stream. This means that we might receive partial bytes from Redis command or receive bytes from multiple commands in the same read. The dissipate method extracts a comment from the buffer, but it doesn't mean that there is no data left in the buffer. So the dissipate command extracts a comment from the buffer, but doesn't mean there is no data left in the buffer. We just loop through each byte into the data buffer, and then we try to deserialize it. We have some complexities over here because there is no guarantee that, for example, a client could send partial wrong information. Okay? Similar to HTTP, where we receive bad requests and return a 400 error, this can happen over here as well. For example, we receive some dump data, and then that dump data is in the buffer, and then we receive a command. This is the data in the buffer. If you try to check just the first byte to see what is the data type, we'll check, okay, this doesn't mean anything, it's just trash, and we would discard everything over here. This is why we do this for loop, because this way we could check, okay, D is not a data type, U it's not, M is not, D is not, A is not, T is not, A is not, asterisk is a no data type. Right now I know that I need to try to deserialize it. It will try, because we have no guarantee that this is correct. Because, for example, right here it says that we have 2 different arguments, but if we receive a request like this, that means that this request is incomplete, because we're expecting 2 arguments. In that case, we can't deserialize. The deserialization fails, and that information will be left in the buffer until we receive further the rest of the information. Once we have all this information in the buffer, the serialization will succeed, and that's what's going to happen over here. It's complex, it's not easy to fully understand it. You need to debug and you need to play with different data types, but that's the main idea. And last but not least, we are going to take a look into the snapshot implementation. To recover, to restart snapshot, we first need to save the snapshot. That's the first thing that we are going to look. We have this function periodically save snapshot. I put in a Go routine, so it's not going to block anything from the performance of executing the redis commands. And the function is just an infinite loop that will execute after 5 seconds, and we execute this function save snapshot. Our data structure is a cache that is a map, so we have keys and values. In Go, I needed to implement as this sync map, because cache from the sync package is a concurrent safe map. But why do we need to do that? Because we have concurrency, we have many connections, many different Go routines trying to access, change the map data. Regular maps in Go are not safe for those concurrent reads and writes, and will panic. Go will not allow us to do that. It returns this fatal error concurrent map writes. This sync map is a package that ensures the safe access for concurrent operations without requiring manual locking like mutexes and other complex implementations. We just need to create a file to store our binary data, and my implementation is really simple. I'm just going to get each different key and value and separate it with this /any type of character, and that's it. Simple like that. At the beginning I was tempted to try to use a JSON or other types of text values, but I don't think that makes sense, because in the end, if we transform that into a JSON file and asks that JSON file to be stored in the database, that JSON file will be converted to binary. The thing is, when we have this JSON file, it's an easy format to restore. Okay, but it's going to use more data, because JSON was designed to be human readable, so we have those curly brackets, we have those double quotes. Implementing our own protocol to save this data would be a better case and an opportunity to implement something fun that we usually don't do. I just think that I did this when I on college, probably, but it was a long time ago. I have an example here of this problem of why JSON would took more values, more space. Because, for example, if you have 2 keys A and B with val1 and val2 values respectively, the saved file would have the a/n val1/n b/n val2 value, or this binary over here. If we're going to save it as JSON, you would have those different characters that I mentioned before, probably white spaces, despite we could remove the white space and so on. But anyway, I'm just like thinking about it. I didn't any benchmark to prove that, but I think that's the case, and that's why some protocols like protobuf were created. To restore the snapshots, we just need to split the /n, which is this byte over here, and that's it. Because from the first byte to the first /n is going to be the data of our first key, and then from the first /n to the second /n is the first value. Simple like that, and so on. We don't need the text format like JSON at all. And Redis also have its own protocol to restore data and save those snapshots, but I was too lazy to do that, and I actually wanted to think about the problem and created my own. Probably there is problems with this implementation, but it was fun to implement it. And the restore snapshot logic will be simple as I describe it in the text over there. We are going to open the file, and then we start like to scan the data, and then we just get text from the scanner. As we use the /n as a separator, the scan is going to handle it, but we need to check that. Maybe you can test right now, right? You guys have not seen that thing working. Let's build, let's run. All right, we have seen this message because we don't have the snapshot gedis, but we already have it since the 5 seconds passed. And I will set a couple of values. So let's just put 2 different keys. It will be the key 1. We'll have the val 1, and the key 2. You have the val2, right? And if we return the key 2, we have the val2, and the key 1, we have the val1. Awesome. Now I will stop the server and we'll start again. And we have the Redis val1 and val2 perfectly. It's nice to implement a benchmark to compare with the original implementation, which is written in C. It's working, it's running, and then with the redis-cli, we have the benchmark. Let me get, I believe this one is a good one. Let's put more zeros over here, and that's it. So we got this result for the original Reds. Now I will stop. I will run my implementation and run the benchmark again. Yeah. Half of the performance. I'm a terrible programmer. Even with all the bloat of having all those other features, Reds is better. But it was fun to implement it. I think I had a better implementation, or I had with a different benchmark. Let's do it. Let's decrease the number of concurrent operations. I will stop my server and start. the Redis serves. And then let's just remove 1 0. And let's stop the red service again, run my own implementation, and run the benchmark again. Oh, okay, we are closer right now. If I'm not mistaken, Redis runs in a single thread, and I implemented each one of the connections in a different Go routine. I tried to remove it, but the performance was terrible. I don't know how they could do that like in a single thread. If anyone knows why this is better and how we could improve this code, just left in the comments or just open a pull request on GitHub, because that's a mystery to me. But that's it, guys. We have this zoom out vision of the mind mapping of everything that I learned by implementing the Redis server. It was awesome to do that, and more awesome to be able to share that with you. Any wrong information that I spread in this video, something that we do not agree, feel free to left your comments down below over here, and we can talk together and discuss and learn more. That's the objective of this video. Okay, see you next time. Bye.